This is lecture 23. I don't have a class here because I'm doing an extra lecture. It's advising day for the students here in 2018. But I left for spring break early, so I decided I want to get an extra lecture in. And for those who are taking the class here in 2018, on Friday, 2 days here, you will be quizzed on some of the material for this lecture. So lecture 23, I do want to say a little bit more about group theory. I said lecture 22 was going to be the last thing about group theory, but I want to say a few more things about group theory that I think need to be said. So a few more remarks about advanced topics in group theories, more ideas for foundations of math topics if you need to take that next interim. Also, the main topic of lecture 23 is going to be an introduction to rings, both the definition of what a ring is and examples. On Friday, lecture 24, we'll get into some basic proofs. All right, so in the last lecture, lecture 22, I did give a brief overview of the fundamental theorem of finite abelian groups. This is, again, something that I could probably spend 4 lectures on if I wanted to do it really in depth. Let's quickly review what it is, and then I want to show you some Mathematica code I found off the Wolfram Demonstrations Project to illustrate this. So the statement of the theorem, again, says this. It says, every finite abelian group, focus on the word abelian, okay? This only applies to abelian groups, is a direct product. It doesn't say external or internal. It could be either because they're isomorphic to each other. If you write a group as an internal direct product of subgroups, it will be isomorphic to the corresponding external direct product of those same subgroups. Of cyclic groups of prime power order. Okay, so the factors in the direct product are cyclic groups whose orders are a power of a prime, based on the prime factorization of the order of the group itself. Moreover, the number of terms in the product and the orders of the cyclic groups are uniquely determined by the group. Didn't fix that typo. That should be determined, not determined. Again, proving this is very challenging. The text breaks it down into a sequence of lemmas, which are little helpful facts to organize a proof, to help you understand it better. It's worth doing, and again, you could do it for foundations of math. The theorem can be generalized to what are called finitely generated abelian groups that are not necessarily finite in number. The order could be infinite, but they somehow could be finitely generated. Z, the integers, is one example of a finitely generated abelian group. And there is a corollary of it that does take some proof. It's not immediate. This corollary is not immediately obvious. If G is a finite abelian group, this is a partial converse of Lagrange in that case, and M divides the order of G, then G does have a subgroup of order M, at least one such subgroup. All right, I did outline steps for putting this theorem into practice as far as what you need to know. My students, given an abelian group with order n, we wish to find the possible isomorphism classes of G. Step 1, find the prime factorization of n. Step 2, find the number of partitions of the positive integer powers of these primes. And again, say we take an example here. Let's say n is 144, for example. 144 is prime factorization. Let's see, if 144 is 12 squared, and 12 is 2 squared times 3, so we're going to get 2 to the 4th times 3 squared. We need to look at the number of partitions of the powers of these primes, the 4 and the 2. What do I mean by that? The partitions of 2, consist of those sums of positive integers that give you 2. Well, there's 2 itself, a sum of one thing, and there's 1 plus 1. So there are 2 partitions of 2. As the exponent goes up, the number of partitions goes up. What are the partitions of 4? There's 4 itself. There's 3 plus 1. There's 2 plus 2. There's 2 plus 1 plus 1. And there's 1 plus 1 plus 1 plus 1. I could, of course, also write 1 plus 3, and 1 plus 1 plus 2, and 1 plus 2 plus 1. But we don't think of those as being distinct partitions, and that's good for the purposes of this theorem because, again, in an external direct product, it doesn't matter what order you put the factors in, you get the same isomorphism class. So there are 2 partitions of 2, and there are 1, 2, 3, 4, 5 partitions of 4. Altogether, that's going to mean there are going to be 2 times 5, 10 isomorphism classes for abelian groups of order 144. We will see that in a second here. Yeah, multiply those numbers, 2 times 5, to find the total number of possible isomorphism classes, and then you write them down using the method that I showed you in lecture 22. But here in this lecture, I'm just going to show you this Mathematica. So again, I got this off the Wolfram Demonstrations Project. It's not my code. I will give credit to the person who created this. Go down at the bottom of the notebook here. The author's name, if you want to zoom in there, is named Mark Brody from Wheeling Jesuit University. Okay, so that's the person who created this code, but it was on the Wolfram Demonstrations Project. It's something that can be downloaded. And what does this code do? We don't see the code here, it's hidden in the background, but you can see some of the output. And let's look at this output right here. We've got to manipulate animation that changes the order of the group, and zoom in if you need to there, order of the group, and it's set to be 144, that's why I picked 144 there. And it's giving you output that says up to isomorphism, the finite abelian groups of order 144, which is 2 to the 4th times 3 squared, are these things. How many of them are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 times 5, just like I said. And as far as the theorem goes, remember it says write these things as external direct products of cyclic groups of prime power orders. That's what we see on the left here. By the way, the x's is, again, as I've mentioned, a common way to write external direct products that our book does not use. Our textbook is Gallian's book, which uses the O plus symbol for the external direct product. Actually, other authors use that for something called an external direct sum, which is related, but I won't get into that. Many authors use an X, really emphasizing that these external direct products can be thought of as Cartesian products. And again, a few lectures ago I did talk about what that was. But do notice, zooming in all these here if you need to, each order of each of these factors is a power of a prime. So we have Z16 external direct product with Z9. 16 is 2 to the 4th, 9 is 3 squared. We would also have Z16 with the external direct product of Z3 and Z3. Right? There's the power of 3 here. 3 squared is 2. There are 2 partitions of 2. 2 and 1 plus 1. 9 is 3 squared. That corresponds to the partition 2. 3 is 3 to the 1st, so we have 2 Z3s. That corresponds to the partition 1 plus 1 as being one of the partitions of 2. And notice it is oscillating back and forth between, as far as the factors that involve powers of 3. Between Z9 and the external direct product of Z3 in itself, it oscillates back and forth here as you go down the list here. There, and there. And then with the powers of 2, the method here is starting off with Z16 in 2 spots here, 2 to the 4th power, corresponding to 4, being one of the partitions of 4. Then in the next 2, you've got an 8 and a 2, 2 to the 3rd and 2 to the 1st. The powers are 3 and 1, corresponding to 3 plus 1, being a partition of 4, occurring again in 2 spots. Here we have 4 and 4 in 2 spots. The exponents are 2 and 2. 2 plus 2 is another partition of 4. Here we have 4, 2, and 2 in 2 spots, these 2 spots here. The powers are 2, 1, and 1. 2 plus 1 is another partition of 4. And finally, you have 2 of these where you've got 2, 2, 2, and 2. The exponents are 1 plus 1, 1, 1, 1, and 1. 1 plus 1 plus 1 plus 1 is another partition of 2. And as I've also emphasized in lecture 22, that's the way it's stated in the theorem, but these can be rewritten. We can rewrite the isomorphism classes using the fact that when the orders of these cyclic groups are relatively prime, they can be combined. You can multiply those orders. 16 and 9 are relatively prime. 16 times 9 is 144. This thing is isomorphic to Z144. It really is a cyclic group. That's the symbol for the isomorphism class that this notebook is using here. In this one, you can combine the 16 and the 3 to get a 48. Here you can combine, you have choices. You could combine the 2 and the 9 or the 8 and the 9. It's more standard to combine the bigger ones. The 8 and the 9 combined to give you a 72. Here you combine the 8 and the 3 to get a 24, and you combine 2 and 3 to get a 6, etc. Here you're more writing it in the fewest number of factors of the external direct product. And you also can note, it's pretty interesting to see, that in each situation, then if you go from right to left, the numbers on the right divide the numbers that go on the left. So 3 divides 48, 2 divides 72, 6 divides 24, 4 divides 36, etc. 12 divides 12. 2 divides 2, which divides 6, which divides 6. That's a standard kind of presentation of these things as well. This would be simpler as far as figuring out number of elements of various orders using the least common multiple condition. Okay, so that's what that notebook does. I want to show you something that I did as well yesterday. I made a little Mathematica thing here. This was something that I did to think about integer partitions. Mathematica has a built-in command called IntegerPartitions, which, for example, can tell you the integer partitions of 4. So the output here should be understood as saying 4 is one of the integer partitions of 4, so is 3 plus 1, so is 2 plus 2, so is 2 plus 1 plus 1, and so is 1 plus 1 plus 1 plus 1. If you, let's do it for 6 here and see how many there are for 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 integer partitions of 6. You can pause the video and double check those things. We can also use Mathematica's length command to find out how many integer partitions there are. But those can be combined in one command. Mathematica calls it PartitionsP to tell you the answer without using two separate commands. Integer partitions and length can be combined, or we can just use the one built-in command, PartitionsP. As you might expect, the number of partitions of an integer goes up. As n increases, you can make a discrete plot of this. A little interesting historical footnote of this is very much related to some things that Ramanujan worked on back about 100 years ago with Hardy, I think it was, very famous mathematician from India who discovered a lot of formulas. He discovered, if I remember correctly, the formula for this as a function of n in terms of simpler functions that can be calculated, but it's still a very complicated formula. And that was a very amazing advance in math, and if you take foundations in math, you'll probably learn about that. As far as another example, with bigger numbers, I thought of this particular factorization, this particular number, which to find it, I wrote the prime factors and raised them to various powers. By the way, factor integer can go in reverse and factor the given number to see that it's 2 to the 6 times 3 to the 4th times 5 squared. And if I use partitions P in the way that I described in the slide, multiply them, multiply the number of partitions for each of these powers, 6, 4, and 2, I can get the number of abelian groups of order, in this case, 129,600. And that would be 110 abelian groups. That would be the number of isomorphism classes of abelian groups of order 129,600. I also made a little bit of code, my own Mathematica function here, to compute that for an arbitrary input, like 129,600, like 72, or like 144. Should get 10 here. So this code, not sure if it's the most efficient code, but it does compute the number of abelian groups of various orders. Okay? And you can copy that down if you'd like to make use of that if you would like to. Let's also highlight some other things. I did, at the end of lecture 22, talk about the Sylow theorems. Let me talk about them some again. I think it's worth re-emphasizing some facts about those again. I did also have this slide about showing that any group of order 35 is cyclic. I went through this argument in lecture 22 if you're interested. I would encourage you to look through it again. And in fact, maybe even pause this video and watch lecture 22, or at least this part of it, because what I'm about to show you is an application of Sylow's third theorem here in a few minutes. Let me jump to Sylow's third theorem. Okay, so what does Sylow's third theorem say? We're going to look at an application of this. Actually, let's think of it in the context of a group of 144 here initially, which we've already seen is 2 to the 4th times 3 squared. Okay, so look at this theorem. If you got a group G, it's finite, it's got order p to the k times m, where the greatest common divisor of p and m is 1. What would that mean, by the way? That would mean m has prime factors other than p. And in fact, k is the highest power of the prime p that divides the order of G. Those are a couple things that would mean. Then what's the number of Sylow p subgroups? The possible number of Sylow p subgroups. The theorem claims it's either equal to mod, well, it equals mod 1 mod p, and it also divides m. Also, any 2 Sylow p subgroups are conjugate. This is where lecture 22 would be good to look at if you have no idea what this is talking about. I will briefly say what it means in the context of an example of a group of order 144. The prime factors of 144 are 2 and 3. So the possible kinds of Sylow p subgroups are Sylow 2 subgroups, which would have order not 2, but the highest power of 2 in the prime factorization. If you look at this definition up here, that's what that would tell you. 2 to the 4th is the highest power of 2 in the prime factorization of 144. So any group of 144, abelian or not, this applies to non-abelian groups too, the Sylow 2 subgroups would have order 2 to the 4th, 16. And Sylow's first theorem would say you've got subgroups of order 16. There is at least one Sylow p2 subgroup. Sylow 3 subgroups have order equal to the highest power of 3 in the prime factorization. 3 squared is 9. And you got at least one of those. There are no other Sylow p subgroups here because there's no other prime factors of 144. But what does Sylow's third theorem say about the possible numbers of Sylow 2 and Sylow 3 subgroups? Focus on the Sylow 2 ones first. Take the p to be 2 and the m to be 3 squared, 9. K would be 4. Looking at that prime factorization at the same time here. The theorem says the number of Sylow 2 subgroups would equal 1 mod 2. So it would be an odd number. And it would have to divide m, it would have to divide 9. So the number of Sylow 2 subgroups equals either 1 or 3 or 9. This marker's going on at me. Number of Sylow 3 subgroups by the theorem has to be odd because it has to equal 1 mod 2. And it has to divide m, which is 9. 1, 3, and 9 are the only positive odd numbers dividing 9. So it's got to be one of those. Which one? We don't know yet. Maybe it could be all of them, depending on the group. Well, how about the number of Sylow 3 subgroups? Take p to be 3, k to be 2, and m to be 16. So the theorem would say the number of Sylow 3 subgroups has to equal 1 mod 3. That would have to be 1 or 4 or 7 or 10 or 13, etc. And divide m, divide 16. The only possibilities are 1 or 4. That both are equal to 1 mod 3 and divide 16. Okay, so that's what I would say for a group of 144. And then you could maybe figure out some other things based on this. Now, what's most interesting, or at least maybe not most interesting, but the thing you can typically do with this is if it's a situation where you can show there's exactly one Sylow p-subgroup of a given order, it would have to be the unique one. And because of that, it would turn out it would have to be normal in the group, because of the conjugacy definition and the fact that two Sylow p-subgroups are conjugate. It would mean if there's a unique one for a given p, it would have to be normal in the group. And that's significant, because then you can form factor groups and then you can analyze things. And I'm going to show you an example of that here in a minute. If you're interested, you can look in chapter 24 of Gallian's book. I've got these pages. It's the 9th edition here in 2018 is what I've got here. It looks like this. You can look into seeing how the Sylow theorems are applied to figure out these facts. One of which I want to highlight is any group of order 15 is cyclic, even though 15 is not prime. It's interesting. We saw groups of order 35, even though 35 is not prime, are unique. They must be cyclic as well. A group of order 99 must be abelian, not necessarily cyclic. And there would be two possible isomorphism classes. Let me just highlight one final thing here. Any group of order 255 is cyclic. Now, I'm going to show you in the next slide the argument for that. I'm not really going to go through the argument in detail because it's pretty similar to the argument I gave in lecture 22 about showing that groups of order 35 are cyclic. So once again, looking at lecture 22 would be helpful for this. Here is the outline of the proof. You can certainly pause the video and look over this. And the thing that I would highlight here is that this argument is very similar, except we're using the Sylow theorems. We didn't use the Sylow theorems for showing that the number of any group of order 35 must be cyclic. Here, for a group of order 255, which is prime factorization of 3 times 5 times 17, and you're going to have Sylow 3, Sylow 5, and Sylow 17 subgroups. We do need Sylow's third theorem, as you can see right away. But you also see, as you look through it, things from lecture 222 come up, like the NC theorem. We're talking about the normalizer of H mod the centralizer of H being isomorphic to a subgroup of the group of automorphisms of H. And since H here is a Sylow 17 subgroup, it's got order 17. It must be cyclic. It must be isomorphic to Z17. And the group of automorphisms of Z17 is isomorphic to U17, which has got 16 elements. The center comes into play as well. The GZ theorem comes into play. It's beautiful. It's just, even the fundamental theorem of finite abelian groups comes into play. It's beautiful. All these different tools coming together to prove that any group of order 255 must be cyclic. Right? That's pretty amazing. How would you ever guess ahead of time that a group of order 255 would be cyclic? And how would you ever guess that just based on the axioms of group theory, the definition of group, that's what I mean, you know? You got a binary operation, satisfies closure, associativity, existence of an identity, and existence of inverses. Who would know you could do such a thing? It's amazing. Okay, I praise God for that. That's just something that makes my heart sing to look at all that and how everything comes together to be able to prove such a thing. That's the thrill of group theory. Okay? I would also encourage you, before I go on to look at some other chapters briefly, to look at page 397, and they list out the possible isomorphism classes of groups of various orders up to order 100. And you know, one of the orders that give you a large number of isomorphism classes, they are, in this chart, at least the powers of 2. For example, there are 267 groups of order 64 up to isomorphism. Okay? Powers of primes, 3 to the third, for example, or 3 to the fourth would be a large number of groups as well. 81, 15 groups of order 81, not as large as I was hoping. I'm sure groups of order 243 would be large. That would be 3 to the fifth. Group of order 96, there's 230 of those. Okay? So mathematicians have worked real hard at classifying the total number of groups. Which brings us to another advanced topic. This is going to be real brief, but I hope enticing. Another advanced topic in chapter 25 is the idea of something called the simple group. A group is simple if its only normal subgroups are the trivial subgroup and the group itself. Now, the most simple groups are indeed very simple. And they are building blocks. They are the cyclic groups of prime order. Okay? The trivial group as well as cyclic groups of prime order are simple. And those are certainly very simple groups indeed. But the name simple group is a little bit of a misnomer. It's a little bit misnamed, I think. It's historical. But non-abelian groups are paradoxically, well, hard to find and can be complicated. Not necessarily real simple to understand, is what I mean. In fact, the smallest non-abelian simple group has order 60, and it is our old friend A5, the alternating group on 5 objects. It's got order 60, right? 5 factorial divided by 2. And it is the smallest non-abelian simple group. This has real big historical significance, mathematically speaking. It goes back a couple hundred years ago to Galois, which, by the way, is spelled, Galois was French. It looks like Galois, but do not say Galois, okay? Say Galois. Galois discovered that A5 was simple, though he didn't use our abstract group theory approach. He was thinking in terms of groups of permutations. It was concrete. And that was historically important because it ended up showing that a quintic equation in general, a 5th-degree polynomial equation, cannot be solved by radicals. There's no simple formula in general for solving a quintic equation. That was a historically very important thing. The classification of non-abelian groups, non-abelian finite simple groups, is one of the biggest things that has ever been done in math. It's one of the most monumental efforts in the history of mathematics and science, which, with hundreds of mathematicians working for many years, producing thousands of pages of work to try to classify non-abelian simple groups, finite simple groups. Okay, they worked a long time, starting around, I think, in the 1950s, 1960s or so. They thought they had finished it in the 1980s, but they found that they weren't quite finished. It's only been finished here essentially since about, I think, 2004, if I recall correctly. It is 2018 right now. So that was an amazing thing. And yes, chapter 25's got some history of that, and I would strongly encourage you, if you like group theory, to look into that, to get a little feel for what that's about. Here's a real brief overview of some more advanced topics. Chapters 26 and 30, separated there, are about generators and relations and Cayley digraphs. Generators and relations are ways of representing groups, and Cayley digraphs, well, symbolically. And Cayley digraphs are ways of representing groups visually. That's why I lump these together. And in there, you're going to see the classification of all groups through order 15, which is, you know, enough for us as an undergraduate course, if you were looking into that. Characterizes all dihedral groups. It turns out this has also got importance outside of math. It's important in physics. And it also turns out to be important in computer science. Chapters 27 through 29 are about symmetry groups, frieze groups, and crystallographic groups, and also symmetry and counting. It's important in art and crystallography. And crystallography is important in the discovery of the structure of DNA. The author does talk about how that was, group theory was actually helpful in discovering this double helix structure of DNA, and in general in understanding molecular structure. Chapter 31 is about algebraic coding theory, error correcting errors in noisy codes, transmission, so it's about signal processing, sending messages, and correcting any errors. And chapters 32 and 33 are on Galois theory and cyclotomic extensions. Essentially, that's the advanced theory of polynomial root finding, you might say, or proving things about polynomial root finding, like the fact that quintics don't have a general formula for their roots in terms of finding, you know, rational functions of roots, that kind of thing. You know, there's no real advanced generalization of the quadratic formula for quintic equations. We might be able to have time to get to Galois theory a little bit in this class. If we do, it'll be a real light treatment, kind of like we're doing with the fundamental theorem of finite abelian groups. All right, now we're on to the main topic for the lecture. Are we on time? Okay, that took a half hour. All right. So a half hour for this. What I want to do here in lecture 23 with a ring is first just define it and make some comments about the definition, and then just look at examples. Okay? And on Friday we'll look at some basic kinds of proofs as well. So, what's the definition of a ring? First of all, the most basic thing is you've got two binary operations. A ring R is a set with two binary operations called addition and multiplication. And, you know, most typically it's sort of what you would call ordinary addition and ordinary multiplication of the objects involved. You can come up with strange things too, but that's not the most typical kind of thing to think about. They are binary operations, so as I emphasize with groups, that means you got closure automatically of both addition and multiplication. Okay, I could emphasize that by saying closure, but that's implicit in our textbook's definition of binary operation. It's got some other properties as well. Now the book lists out these properties in a fairly large list, not super large, but somewhat large. Let me glance at it here. It's on page 227. I guess they list 6 things that go beyond what I've said. And they list them symbolically. I'm going to describe the properties verbally. Okay? But they mean the same thing, and you'd be able to think of it either way. The first property is that R is an abelian group under addition. All rings have addition be commutative. Okay? And we don't use E for the identity element. We use 0, as we have always done when the operation is addition. E in group theory is our generic identity element signifier, symbol. Though in general, when we were talking about abstract group theory, the operation was assumed to be multiplication. Though with examples, the operation could be addition. And in those contexts, we called the identity 0, and that is going to be consistent here with rings. 0 will be the additive identity always for rings. So it's an abelian group under addition. It's not an abelian group or even a group under multiplication. But it does satisfy some properties related to multiplication. First of all, closure. Secondly, the associative property for multiplication does work, as it works for addition, because it's an abelian group under addition, and we know groups that satisfy the associative property. So here's the associative property for addition. So the fact that it's a group under addition means it's going to satisfy that. And the multiplication does satisfy the associative property, so I can write this as well. The addition is the group operation, not the multiplication. Multiplication is not group operation. No ring is a group under multiplication, though some rings are groups under multiplication if you take out 0. That's worth saying again, actually. No ring is a group under multiplication, though some rings are a group under multiplication if you take away 0. That actually shouldn't be surprising, because some of the examples we talked about are groups under multiplication included, for example, the real numbers take away 0. The left and right distributive laws hold. Without peeking in the book, maybe you want to pause the video and write down what you think that means. Distributive law relates addition and multiplication. Here's the left distributive law, where the single element is being multiplied on the left. And here is the right distributive law, where the single element is being multiplied on the right. By single element, I mean the A here and here. So it's relating addition and multiplication. And by the way, we're not going to assume the group is the ring is commutative under multiplication in general. So in general, these are not the same thing. Here are some remarks, including what I just said. Rings do not have to have a multiplicative identity, at least in our author's definition. Some authors require a multiplicative identity, but I think our author is choosing the best route here, my personal opinion. I think it is best to not require a multiplicative identity because otherwise certain examples that you might want to be rings would not be rings. Example of which we'll see shortly here. So there need not exist an identity, a multiplicative identity. There's an additive identity. 0 is always in there. When there is a, excuse me, when there is a multiplicative identity, that was bad. I don't know where that came from. We denote it by 1. By 1. Or maybe sometimes I for like identity matrix. Or maybe ID. Typically denoted by 1. And we can call it a multiplicative identity, but for short, we typically call it a unity. Really, the unity. If there is an identity, it does turn out to be unique. Though that uniqueness is with a little bit of a caveat, as we're going to see. So you could really call it the unity. Just remember, unity means identity, multiplicative identity. Even when there is a multiplicative identity, there need not be multiplicative inverses. An element that does happen to have a multiplicative inverse is called a unit, for short. So unity means 1, means the multiplicative identity. Unit means it's got a multiplicative inverse. There's only one unity, but there could be lots of units. There could be lots of elements with multiplicative identities. And for example, take the real numbers, subtract away 0, or group under multiplication. Every element is a unit in that case. We've taken away 0. 0 couldn't possibly be a unit because there's nothing you could multiply by 0 by to get 1. So that's part of the reason we take away 0. Multiplication need not be commutative. When it does happen to be called commutative, we say it's a commutative ring. We do not say abelian ring. Don't say abelian ring. Abel's got enough credit. You know, Abel was a great mathematician. And there's something called the Abel Prize you might want to look up. And Abel has a abelian group named after him. Abel, by the way, was a contemporary of Galois a couple hundred years ago. Don't say abelian ring, okay? It's a commutative ring when multiplication is commutative. Again, addition is always commutative. You can always say a ring is abelian, an abelian group under addition. But when you say the ring is commutative, you mean the multiplication is commutative. AB equals BA for all A and B in the ring. All right, here's some initial examples. And an important takeaway from these initial examples, weird things can happen in rings. Okay? This abstract definition encompasses many examples as good abstract definitions should. And in many of these examples, weird things do happen. If we restrict the definition a little bit more, if we add more conditions, so the ring is more special, like commutative, or maybe like the fact that every non-zero element has a multiplicative inverse is a unit, then that restricts what can happen, and then weird things don't happen so much, at least. Both Z and Zn are commutative rings with unity under the expected operations. Z is a ring under ordinary addition and ordinary multiplication. It's a commutative ring with unity. It's got 1 in it. The number 1 would be the unity. What are the units of Z? Think about that. There's only 2 of them. 1 and -1 are the only units of Z. Zn has ordinary mod n addition and ordinary mod n multiplication defined in it to make it a commutative ring with unity. I am assuming n is bigger than 1 here. I didn't say that, but I am assuming implicitly n is 2 or bigger. However, Zn is weird when n is not prime. How so? Let's look at the multiplication table for, say, Z4. I'm not going to call it a Cayley table because it's really not a Cayley table, because Z4 is not a group under multiplication. So this table is, in some senses, going to be weird. The elements are 0, 1, 2, and 3. I am doing multiplication mod 4 here, not addition. So this is not going to be a group. It's not a Cayley table. 0 multiplied by everything. This takes proof. The book does prove it. 0 multiplied by anything does give you 0. And in fact, we already knew that with mod 4 arithmetic. So you get a bunch of zeros here. And right away, it's weird. Okay? This column and this row have all the same elements in them. And that never happens with Cayley tables for groups. So right away, it's weird. You might say, well, let's take out 0. But there's still some weirdness here. 1 is the multiplicative identity. 1 times anything is itself. We do get this, so this doesn't look so weird. But 2 times 2 is 4, which is 0 mod 4. We get another 0 in that row in this column. That's a weird thing. 2 times 3 is 6, which is 2 mod 4. So we get another 2 in this row and this column here. Again, that's not something that we typically have in groups. Finally, 3 times 3 is 9. Mod 4 is 1. Another weird thing here is the 1 only occurs twice in the Cayley table, in the multiplication table. Okay? So there's a few weird things that are happening. I could consider more examples, but I think for the sake of time I won't. I would encourage you to consider other examples like, say, Z6, and look for other weird things that might happen. For example, look for the cancellation law not working. In general, for rings, there is no cancellation law for multiplication. And you'll see that in the reading. If n greater than 1 is an integer, then the following set is a commutative ring without unity under the usual operations of addition and multiplication. This set here, the set of all integer multiples of the fixed integer n. So if n is 2, then this would be the set of all even numbers, even integers. If n is 3, this is the set of all multiples of 3. If n is 4, it's the set of all multiples of 4. If n is 5, it's the set of all multiples of 5. Those are all rings, commutative rings. But if n is bigger than 1, there's no unity. There's no 1. There's no multiplicative identity here. And this would be the simplest example of something that I would want to call a ring, and our author would want to call a ring. But some mathematicians who require rings to have unities would not. So I would like to include this in the category of what we're calling a ring. And that's what we will do. Could I call this, could I denote this by this symbol? Well, maybe. And as a group, as an additive group, you could certainly denote it by that. But for the moment, we won't. For the moment, we'll denote it by NZ, which makes some sense with some of our previous notation. An even weirder example is that the following set is a commutative ring with unity under addition and multiplication mod 10, but the unity is not the number 1. What in the world is this set? It's 0, 2, 4, 6, 8? Really? That's a commutative ring with unity. There's no 1 in there. How could there be a unity? Well, one of the other elements is acting like the unity. And this is getting at the caveat that I need to mention with regard to what really is a unity. If you do a little experimentation, you quickly see that 6 is the unity. 6 times 2 is 12, which is 2 mod 10. It's all mod 10 arithmetic. 6 times 4 is 24, which is 4 mod 10. 6 times itself is 36, which is 6 mod 10. 6 times 8 is 48, which is 8 mod 10. And yeah, 6 times 0 is 0, which is 0 mod 10. 6 is the unity here. Weird. But wait a minute. Wouldn't this be like a subring of Z10? There is such a thing as a subring, and yes, there is such a thing as a subring. Yeah, the last two examples are subrings. Just like there's an idea of a subgroup, there's an idea of a subring of the rings above. So if this is a subring of that, how could 6 be the unity? Wouldn't that mean 6 is a unity in here? No, because 6 only acts as a unity on these numbers, 0, 2, 4, 6, and 8. It doesn't act as a unity on other numbers, like 6 times 1 is not a 1, it's 6. 6 times 3, 18, which is 8 mod 10, not 3. 6 times 5 is 30, which is 0 mod 10, not 5. And there's another weird thing. Weird. 2 non-zero things multiplying to give you 0? That's weird. So while 6 acts as a unity on some of the elements in Z10, 1 is the only thing that acts as a unity on all of the elements of Z10. So that's something that is worth emphasizing. The unity is unique, but it's got to act as a unity should on all the elements. More examples where sometimes weird things continue to happen. Let M2Z denote the set of all 2 by 2 matrices with integer entries. That's why we have a Z there. The 2 means 2 by 2. Under the usual operations of matrix addition and multiplication. This is an example of a non-commutative ring with unity. Multiplication in general, as you know from linear algebra, multiplication of matrices is not commutative in general. But this does form a ring. By the way, notice there's no condition about the determinant, like there was for something like this. Right? That was the general linear group of 2 by 2 matrices with real entries, but we said the determinant had to be non-zero. The operation was matrix multiplication. The determinant being non-zero meant that the multiplicative inverse would exist. Here, there's no condition about the determinant. Any matrix, any 2 by 2 matrix with integer entries is part of this ring. And what is the unity? As you would hopefully guess, it is the identity matrix. That would be the unity. In linear algebra, we typically call that I. And it's fine if you want to call it I, but we can also call it 1. Maybe make it a real bold-faced 1 to emphasize the matrix or something. And it's non-commutative. Don't say non-abelian, say non-commutative. Matrix addition is commutative. It's an abelian group under addition. I guess that's not too weird. It's the only the non-commutativity, I guess, that's a little bit weird. But we're used to that anyway. This is the set of all 2 by 2 matrices with entries from 2Z, which is the even numbers. Only even entries. It turns out to be a subring of this. I haven't officially said what a subring is, but it is what you would think it is. It's a subset of the given ring that is also a ring with the same operations. This is a non-commutative ring without unity. The identity matrix is not in there because the entries are not all even. And no other element acts as the identity either. That would technically take curve. Another example, N2Z2 would be the all 2 by 2 matrices with entries from Z2, so just zeros and ones, under addition and multiplication of matrices mod 2, so make sure you just do modular arithmetic there when you do the matrix multiplication. This turns out to be a finite non-commutative ring with unity. And if you think about it, since there's 2 choices for each entry and there are 4 entries, the total number of elements would be 2 to the 4th or 16. I did make some Mathematica code to illustrate this ring. It's not the most ideal code in the world. I'll probably show it to you on Friday. Maybe try to make it better. To illustrate this ring and its multiplication table. And also emphasize that the units in here, there are 5 of them. No, 6 actually. 6 units in this ring. 6 of them have multiplicative inverses. How are we doing in time? About 10 more minutes here, okay. More examples? Where again, sometimes weird things continue to happen. Not too weird here, but okay. It's really that first slide that was the weirdest stuff. For today, at least. Let Zx, with square brackets around the x, not parentheses. Make sure you write it like that. Square brackets around the x. Denote the set of all polynomials with integer coefficients. So the Z emphasizes that the coefficients are integers. The square brackets and the x inside represents the fact that we are saying these are polynomials. And the x is the variable. Should I call it a variable? Well, maybe here initially it's better to call it something else. Indeterminate is a word you could use, which is kind of synonymous with variable anyway, but it might be a better word than variable. At least at the moment, I don't want to plug in any number for x. Okay? I just want to think of the polynomials as being objects in their own right, algebraic objects. I don't want to think about plugging numbers in or graphing them, at least initially. Just thinking about the algebra operations of ordinary polynomial addition and multiplication, where with polynomial addition, you combine like terms in the usual way. And with multiplication, you've got to use the distributive property with the terms of the polynomial in the way you've learned in the past. I'm not going to get into nitpicky details about proving things with that. Then this turns out to be a commutative ring with unity. The zero polynomial, and I guess you'd have to define 0 to be a polynomial, is the 0 element, the additive identity. The 1 polynomial, meaning just 1, not as a number, but as a polynomial. That's part of the confusion here. Are 0 and 1, are they numbers or are they polynomials? Well, I'm thinking of them as being polynomials, which also can happen to be thought of as numbers, but they are part of this ring. And they are the additive identity and the multiplicative identity. It's a commutative ring with unity. Let's see. Okay, let's emphasize something more here. So when I say polynomial addition is done in the usual way, I mean if you've got 2 polynomials, 5x cubed minus 7x squared plus 4x plus 3, and you're adding that to negative 2x squared plus 5x minus 6. You'd add these polynomials just like you'd think you would. Technically speaking, the powers of x are just kind of serving as placeholders. And in fact, there's probably a technically better way to think about polynomials in terms of really what you might think of it as external direct products of infinitely many things. It's not really exactly what I said there, but it's related to that. But I'm not going to worry about that, and the textbook doesn't either. just go ahead and add these the way you know you should. Combine like terms. You've got the 5x cubed being the only x cubed term. The x squared terms are the negative 7x squared and the negative 2x squared. You combine those, you're going to get, as you would think, negative 9x squared. 4x and 5x do combine to give you plus 9x, and the 3 and negative 6 do combine to give you minus 3. Multiplying these, I'm not going to do the entire multiplication, but let me just briefly say what you would do. Certainly if you had two binomials, two linear polynomials, you could foil it. But here, you can't foil because you've got a quadnomial and a trinomial. But what you can do is you can take each term, say here over on the left, and multiply times each term over on the right. Really, I'm using the distributive property for polynomials there. I'm assuming that holds. And then you do the same thing with the next term on the left, and then the next term, and then the next term. And then at the end, you combine all the like terms. So 5x cubed times negative 2x squared is negative 10x to the fifth. 5x cubed times 5x is plus 25x to the fourth, etc. Before combining like terms, you're going to have how many things? You're going to have 4 times 3. You're going to have 12 terms. Combine like terms, like powers, which is another x to the fourth term. You combine it with this x to the fourth term. Okay, in the usual way. So, not being super rigorous here, not being super precise, I'm assuming, as the author does, that you know how to add and multiply polynomials in the usual way. And we're not worrying about technicalities or whether or not, we're not going to prove this is a ring. Okay, we're just going to assume you know how to do this. If you restrict your coefficients to being, for example, from Z2, in other words, the only coefficients are 0 and 1, and by the way, by convention, as usual, if a term is missing, if I write something like this, x squared plus 1, there's no x term there, that means its coefficient is 0, like usual. Just understand that. Of course, all the higher powered coefficients are 0 as well. So this is polynomials with coefficients that are either 0 or 1, and the ones that are 0 don't get written down. In an indeterminate x, under, again, ordinary polynomial addition, but again, this time it would be done mod 2. Interesting thing about this ring is it is an infinite set. First of all, even though Z2 only has 2 elements, there are still, if you think about it, infinitely many polynomials you could make. However, in spite of the infinite nature of this ring, every non-zero element has finite additive order 2. You add any element to this, in this ring to itself, you get 0. The additive identity. Does that make sense? If you think of x squared plus 1 as being in this ring, and you add it to itself, you are doing mod 2 arithmetic with the coefficients. So you get 2x squared plus 2, but and I'm okay if you want to write that, but that does equal 0 mod 2. Yeah, and any such polynomial added to itself will give you 0. Each non-zero element has finite additive order as in group theory, 2. Each element is its own additive inverse. Because of this, it turns out in ring theory, we say this ring has characteristic 2. And you can look ahead a little bit, I think it's in chapter 13, if you like, for the definition of characteristic. Yeah, it's on page 240, if you want to look there. Okay? We'll consider other examples of that as well. Real quick, I think this is the last slide. Something called the Gaussian integers you should become familiar with. This following set forms a commutative ring with unity that is a subring of the ring of complex numbers. Complex numbers form a ring, and the real numbers and the rationals. You might say kind of boring rings, nothing too weird's happening, but they do form rings. Under ordinary addition and multiplication of complex numbers, I here is taken to be the imaginary unit, I squared is -1. This is the set of all complex numbers of the form a plus bi, where a and b are integers. The complex numbers themselves are the set of all things of this form where a and b are real numbers. Here I'm restricting a and b to be integers. This is called the Gaussian integers. The notation here is somewhat similar to the notation zx from the other slide, except it is understood here that I is the square root of -1. Now, technically speaking, it is actually consistent with that other notation. We could think of creating polynomials in I that would involve I squared and I cubed and I to the fourth, etc. But as you might guess, if you know about complex numbers, if I squared is -1, then I cubed is -I, and I to the fourth is +1, and I to the fifth is I. All those such polynomials can be simplified down to something that's linear in I. So it is really consistent with previous notation, but it's understood that I squared equals -1. So you can do that kind of simplification. And finally, final example for this lecture is the rationals with square root of 2 adjoined, whatever that means, forms a commutative subring with unity of the ring of real numbers, and the ring of complex numbers for that matter. What is this rationals with the square root of 2 adjoined? It's this set. Set of all real numbers. Oops, a typo here. This computer doesn't have math type installed, so I can't change it here. Well, there is a typo here, okay? I just copied and pasted and didn't make the appropriate change. This I should be a square root of 2. Set of all real numbers of the form a plus b times square root of 2. There's no I involved. So ignore this. Change that to a square root of 2. These are all real numbers. A and b are rational. Square root of 2 is real, not rational. This turns out to be a ring. In fact, it is a ring where every non-zero element is actually a unit. It does have the number, it does have a unit. 1 plus 0, the square root of 2, is equal to 1, and that is the unit. And every non-zero element of this does have a multiplicative inverse. That's something that might be worth your time to check on your own. See if you can figure out, for an arbitrary element, a plus b square root of 2, where a and b are both non-zero, what the multiplicative inverse is that's still in this set, still can be written in the form something, a rational number plus a rational number times square root of 2. Okay? Take that as a little exercise to do before Friday. And that'll be the end of this lecture.